Welcome to The Explainer. Today, we're diving into a really groundbreaking paper called RELIC from the folks over at Google. They've built a new model that promises to turn any single static image into a real-time, fully interactive, and explorable world. I mean, this is the kind of stuff you see in sci-fi movies, but it's happening right now. So let's get into it.
All right, so here's the plan for today. First, we're going to tackle what I'm calling the world model dilemma. It's really the core challenge here. Then, we'll get into the secret sauce, and that starts with the data. They did something really clever with Unreal Engine. After that, we'll dissect the architecture itself, specifically how it solves this huge memory problem. Then, we'll see how they trained it to be super fast, for real-time interaction. And of course, we've got to see how it stacks up against the competition. Finally, we'll zoom out, look at the big picture, and talk about what this means for the future.
All right, let's just jump right in and set the stage. What's the huge problem that RELIC is actually trying to solve? On the surface, it sounds almost whimsical, right? Can you explore a painting? But believe me, from an engineering standpoint, this is a massive, massive challenge. Let's dig into exactly why that is.
So the holy grail, the absolute dream here is to take any image, literally any image, a photo, a painting, whatever, and just step inside. Imagine that. You're not just looking at it anymore, you are in it. You can look around, walk down that path, peek around the corner. But here's the catch. For that to feel real, it has to be instant. It has to react to you in real time. And that right there is where we slam into a giant technical brick wall.
Okay, so this is the heart of the problem. It's this fundamental engineering tug-of-war. On one side of the rope, you have what's called long-term spatial consistency. That just means the world has to feel solid and real. If you see a chair, you turn around, and then you turn back, that chair better still be there exactly as it was. To do that, the model has to remember everything it's already shown you. It needs a massive, ever-growing history of the scene. But, and this is a big but, storing and constantly checking that giant history is super expensive. It takes a ton of memory and a ton of processing power. Now, on the other side of the rope, you have real-time responsiveness. You want to move, and the world has to move with you, instantly. We're talking fractions of a second per frame, and that demands the exact opposite. Low complexity, minimal memory use. See the conflict? These two things are completely at odds. How do you remember an entire world while also being fast enough to interact with it? That is the dilemma RELIC is trying to solve.
So how did they start to unravel this knot? Well, like with so much in AI these days, the solution doesn't begin with some fancy new algorithm. Nope, it starts with the data. And not just any data, incredibly high-quality, purpose-built data. Let's take a look at how they created their digital training ground.
A lot of the older models, they were trained on data that was basically just scraped from video game playthroughs or random videos online. And the problem is, that kind of data is, well, it's messy. It's really biased towards certain things, like just walking forward all the time. The RELIC team knew this wouldn't cut it, so they took a totally different approach. They treated Unreal Engine like their own personal movie studio. They weren't just recording random gameplay, they were directors. They meticulously crafted these camera paths, these trajectories, specifically designing them to loop back and revisit places from different angles. This was crucial because it forced the model to develop a real long-term memory of the 3D space. Think of it this way. It's the difference between grabbing a bunch of random shaky cam footage versus shooting a scene from a carefully planned storyboard.
And they didn't stop there. Even with this handcrafted data, their quality control was absolutely ruthless. They put everything through this intense three-step filtering pipeline. First up, a human had to watch and check the camera movement. If it was too jittery, too fast, or just looked wrong, it was gone. They needed the model to learn movement that felt natural, Second, they did a stability check on the path itself. If the camera clipped through a wall or did something physically impossible, out it went. And third, a render quality check. Any kind of graphical glitch, weird lighting, missing textures, anything, and the video was tossed. What was left was only the absolute best of the best, the cleanest, most perfect data you could imagine.
Okay, so they've got these pristine video clips. Great, now what? A model can't just watch a video, it needs to understand the actions that are happening. The big challenge was figuring out how to take that smooth, fluid camera movement from the game engine and break it down into a set of simple commands the AI could actually learn from. So they built an algorithm that, for every single frame, spits out what's called a 13-dimensional action vector. That sounds complicated, but it's really just a list of instructions. It covers what we call the 6 degrees of freedom, or 6DOF for short. It's just a fancy term for all the ways you can move in a 3D space. Let's break it down real quick. You've got 3 ways to move, or translate: forward/back, left/right, and up/down. Easy.
Then you have 3 ways to rotate. You can tilt your head up and down, that's pitch. You can shake your head no, that's yaw. And you can tilt your head side to side, that's roll. So you've got 3 ways to move and 3 ways to rotate, that's 6 total. Each of those can go in a positive or negative direction, so that's 12 actions. The 13th action, it's just do nothing. Having this precise level of control is absolutely key to making the whole thing feel truly interactive.
But here's where they did something really, really clever. It's a bit of math magic inside this infer pair action function they wrote. See, one of the biggest headaches in 3D AI is something called scale ambiguity. Think about it. If you see a camera move 1 foot, you have no idea if it's moving 1 foot inside a tiny dollhouse or 100 feet across a giant cityscape. The pixels look the same. So how does the model tell the difference? Well, RELIC's algorithm has a brilliant fix. It normalizes the motion. For every single video clip, it first figures out the average speed of movement in that clip. Then, instead of telling the model, move forward 5 pixels, it tells it something like, move forward at 1.5 times the normal speed for this scene. It's all relative. This simple trick makes the model's understanding of movement totally independent of scale. It's an awesome solution that helps it work just as well in a tiny room as it does in a huge landscape.
All right, so we've got the data sorted. It's perfect. Now let's get to the main event, the architecture, the brain of the whole operation. How did they actually build a model that could solve that tug of war we talked about? The one between having a perfect memory and being blazingly fast.
Okay, before we can appreciate RELIC's big idea, we got to do a quick vocab lesson on a key piece of tech called the KV cache. RELIC is a type of model called a transformer, and as it generates new frames, it's constantly calculating how different parts of the image relate to each other. The KV cache is basically the model's short-term memory. It saves the results of those calculations, these things called keys and values, for all the frames it's already made. So when it's time to make the next frame, it doesn't have to start all over again. It can just quickly check its cache. This is a huge reason why modern AI models are as fast as they are. It's a massive shortcut.
So here's where RELIC's genius comes in. A normal KV cache just keeps growing and growing with every new frame. You can imagine that for a long video, that gets out of control really fast. So RELIC does something different. It creates a dual-branch KV cache. And honestly, the best way to think about it is just like our own human memory. The first branch is like your short-term memory. It's a rolling window that keeps the last few frames in super high detail, totally uncompressed. It's everything that's happening right now. Then you have the second branch. This is your long-term memory. As frames get older and leave that short-term window, they don't get thrown away. Instead, they get compressed, summarized, essentially, and stored in this long-term cache. It's not as perfectly detailed, but it holds the gist, the overall structure of the world. And that's the magic trick. It gives the model a crystal-clear picture of the immediate present while also maintaining an efficient compressed memory of the entire past. It's the perfect balance between that speed and consistency we were talking about.
Okay, so we've got the 5-star ingredients with the data, and we've got the master chef's recipe with the architecture. But that's just the plan, right? Now you have to actually cook the meal. And for something that needs to be interactive, you have to cook it fast. That means training and optimizing it for pure, unadulterated speed.
And to get that speed, the team pulled out all the stops. They used a whole bag of tricks. First, this really cool training technique they called palindrome augmentation. Get this. They take a video, play it forward, and then just stick the reversed version right on the end. So the camera goes out, and then it comes right back along the same path. This is an awesome way to force the model to build a memory of what it just saw because it needs that memory to generate the return trip correctly. Super clever. On top of that, they used all the latest and greatest software optimizations. They used something called torch.compile to make their code run way faster on the hardware. They shrunk the memory size of that KV cache by using a lower precision number format called FP8. Basically, they realized they didn't need super high-res numbers, and this one change cut the memory usage in half. They also used custom, highly optimized code libraries like Flash Attention v3, which just makes one of the most computationally expensive parts of the model run way, way faster. And of course, a model this big, 14 billion parameters, can't train on one GPU. They used some really smart techniques to split the model and the data across a whole fleet of GPUs, making the whole process manageable.
All right, the data is curated, the architecture is brilliant, the training is optimized to the gills. The moment of truth. How does RELIC actually perform in the real world? Let's put it up against the other big names in the game and see what happens.
Okay, first up, let's look at the quantitative results, the hard numbers, from a benchmark called vBench. And the results speak for themselves. RELIC comes out on top with the strongest overall performance. But here's what I find really interesting.
Its raw image quality is pretty similar to its main competitor, Hunyu and Gamecraft. But look at the aesthetics score. It's way higher. That's a huge clue that all that effort they put into creating clean, beautiful training data really paid off. The model learned not just to make correct images, but to make nice-looking images. And yeah, it just blows Matrix Game 2.0 out of the water completely.
But you know, benchmarks are one thing. Seeing is believing. The qualitative tests, where you can just look at the output side by side, that's where the differences really pop. So for our first test, let's go to this art gallery. The command is super simple. Just tilt up.
And wow, check out the difference. On the left, that's Matrix Game 2.0. It tries to tilt up, but it clearly has no idea what a ceiling is. It just gives up and generates a big black empty space. The immersion is totally shattered. Now look at the right. That's RELIC. It just works. It smoothly tilts up and reveals this detailed ceiling with skylights. It actually understands the 3D space it's in. It's a night and day difference.
All right, next test. We're in this cool, stylized bedroom with all the neon lights, and this time the command is a little trickier. It's not a rotation, it's a translation. The command is truck left, which is just film speak for slide the camera sideways to the left without turning it.
And again, look at this. On the left, Hunyu Gamecraft just gets it wrong. It confuses slide left with turn left. It rotates the camera like you're turning your head. That's not what we asked for. But on the right, RELIC nails it. It executes the command with total precision. You can see the camera sliding sideways, the perspective shifting just right as more of the room comes into view. This is such a key point. RELIC doesn't just make a pretty video that's kind of close to what you wanted. It does exactly what you tell it to do. That's real control.
So I think it's pretty clear this is a huge leap forward. But, you know, this is science. No paper is ever the final word on anything, and no model is perfect. So let's take a step back, put our critical hats on, and really evaluate the strengths, the weaknesses, and what this all means for the future.
On the plus side, the strengths are just undeniable. The precision control is off the charts, the long-term memory creates these incredibly stable worlds, and it's amazing how well it works on non-realistic stuff like paintings. But, and the authors are totally open about this, it has one major limitation: dynamics. Pretty much all of its training data was of static places, buildings, rooms, that sort of thing, so it doesn't really know how to handle things that move. The worlds it creates are stunning, but they can feel a little frozen. So the next frontier is pretty clear, right? You gotta start training it on videos with moving people, cars, swaying trees, you name it.
Okay, so if you're gonna take away just 3 key things from our deep dive today, make it these. Number 1, curated data is king. That obsessive focus on creating perfect training data wasn't just a nice to have, it was absolutely fundamental to their success. Number 2, the memory problem has a solution. That dual-branch KV cache is such an elegant way to solve that classic tug-of-war between world consistency and real-time speed. And number 3, control is everything. It's not enough to just make a cool-looking video anymore. To be truly interactive, a model has to do exactly what you say, and RELIC has just raised the bar for everyone.
And that really leaves us with one final, kind of mind-bending question to think about now that this technology is becoming a reality. If you could pick any image in the world, any one at all, and step inside it, explore it as a real place, what would you choose? A classic painting? A photo from a vacation? I'd love to hear your ideas down in the comments. Anyway, that's all for us today. Thanks so much for joining this deep dive on The Explainer. If you enjoyed it, please do me a favor and smash that like and subscribe button. It really helps. We'll be back with another paper tomorrow. See you then.